Welcome to your lesson on tangent and normal lines. Let's begin with the big idea, and this is kind of a recap of the journey we've taken so far with derivatives. So we began by talking about the slope. We know the slope or gradient of a line. It's simple. We just find it by doing rise over run, and we know that a line has a constant slope. So no matter where you look on the line, it has the same slope. Then we ask the question, what is the slope of a curve? And the obvious answer is, well, a curve does not have a constant slope. The slope changes as you follow the curve. And the slope here can be represented by tangent lines. You can see the three green lines here. At three different locations on this curve, there are three different tangent lines, and each of those represents the slope at that moment in time. So taking that idea further, we started to derive an equation for finding slope. And we began by taking a secant line, the red line here, finding the slope of that red line. But then as we moved that one point closer to the other, the red line became basically overlapping with the tangent line. So the secant line can represent the tangent line as you move the point closer. We represented that with a limit, showing that the gap between the 2 points approached zero. We created what's called the definition of a derivative. The definition of a derivative is a limit equation that allows us to find a derivative function, which is the slope of an equation. All right, from there we talked about things like this. So let's take a look. Here we have an equation of a parabola, x squared minus x. To find the derivative of that, we have this, 2x minus 1. So there's our original, there's the derivative. Let's say we want the tangent to the original function at x equals negative 3. We want to figure out the tangent line. Okay, so here's the parabola, here's the tangent line. It is really important to say that f prime of x, the derivative function, is not the tangent line. So that's a common mistake made by students when they first learn about derivatives. They say, here's my original, here's my derivative, so I found the tangent line, haven't I? Well, no, because this purple line is just one of infinite tangent lines that are possible. So how could one tangent line represent all the possible infinite tangent lines? It cannot. So the derivative is not the tangent line. The derivative is the gradient function. It is a single function that can tell you the slope at any location. So that's how we're going to use it now. Let's say we want the slope at negative 3. So we want the slope of the curve at negative 3. So we want the slope of this tangent line. So we're going to put negative 3 into the derivative function, right into here. And when you put negative 3 in there, you get negative 7. So the slope is negative 7 there. And we can confirm that. We can draw a slope triangle. We see down 14 over 2. That's negative 7. So we have used the derivative to find the slope right there. Likewise, we could put any point in there to do that. Let's check this out on Desmos. I have something to show you related to this. So here's a parabola as well, and here's a tangent line. And notice here, m is the slope. Right now, this tangent line has a slope of negative 5.8. But as I move along the curve, I have different tangent lines. And the tangent lines represent the slope of the curve at that moment. And look, for example, now the slope is negative 1.2. And then when I go to the bottom of the curve, look, the tangent line is horizontal, and it says m equals 0. There's no slope there. So at that very bottom of the curve, there's no slope. But then as I continue now, it's upward slope. See, upward slope, we have a positive slope now, 1. And I keep going, and the slope is a very steep slope. Now we can see 11.6. So keep an eye on this number here and watch how it changes. As we move along, our slope changes, and the derivative can give us that different slope number as it changes all along the curve as you follow it. Okay, let's go back into here. Let's look at another parabola. So we have a parabola here. Let's say I take the derivative, which is 2x. So now I have my gradient function. That can be used to find the slope anywhere. Let's say I want to find, just a reminder, the tangent, the f of x, f prime of x, the derivative, is not the tangent line, right? Okay, let's say I put negative 2 into f primed, and I get negative 4. That means the slope at negative 2 is negative 4. And then I put 1 into the derivative function, and I get 2. That means the slope when x equals 1 is 2. And let's see those two. So there's x equals 1. There's that line, and that line is going to have a slope of 2. And here's the line at x equals negative 2, and that one is going to have a slope of negative 4. And we can confirm the slopes here and see that. Look, slope negative 4, and here's a slope of 2. All right, so let's do a question. Try this one out. Here is a function. We need to find the gradient function. And then using that gradient function, we're going to find the slope, the gradient of the tangent, which means the slope of the tangent at the point x equals 4. So find the derivative function and then put 4 into it, and you'll know the gradient at that point. Okay, check your work here. Okay, by the power rule, we got this derivative. So check your work carefully. Make sure you know how to use the power rule and deal with exponents and all that. There's a derivative. Then we put 4 into the derivative. It produces the value of 33 over 4. That tells us the slope at that location is 33 over 4. Okay, next. Oh, we should look at the graph. It's always good to look at the graph to see how it works. So the blue curve here is the graph of that function. It's an interesting curve. It goes like that. And then at x equals 4, because that's what we put into the function, x equals 4, there's the tangent line. So that represents the slope. And the slope of that one is 33 over 4, which is about 9 or 8 or 9, right? 8 or so. So that makes sense. That slope looks pretty steep. All right, our goal today, though, is to take this a step further. More than just finding the slopes of the tangent lines, we want to find the equations of these tangent lines. So we can draw these tangent lines. We know what their slope is because we can use the derivative, but then we just want to go ahead and make that a linear equation to represent that tangent line. But we're also going to look at the equations of what are called normal lines. So let's see what those are. First of all, tell me something you notice about these two lines. Well, I hope you said, hey, they are parallel. And when lines are parallel, what's true about their slope? Look at these two equations. And again, I hope you said, hey, their slopes are the same. When two lines are parallel, their slopes are the same. And we can see that here, 3 and 3. Okay, there's the slope, 3 over 1. Here's the slope, 3 over 1. They're the same. How about these? Tell me about these two lines. All right, I hope you said they are perpendicular. When two lines meet at a 90-degree angle, they're perpendicular. And do you know something about their slopes? Here's that line. And this has this slope. What's the slope of this line going to be? Maybe you know this rule. This line has this equation, so notice the slope is 3 over 1. What do you notice? When you have perpendicular lines, the slope is, they are negative reciprocals of one another. They are reciprocals, means you flip it over, and one's negative, one's positive. Important relationship, because that has everything to do with what a normal line is. A tangent line is like the blue one here. We've already been talking about tangent lines a lot. It hits a curve at one point. A normal line is a line that at that same point, the point of tangency, is perpendicular to the tangent line. So you can see the normal is perpendicular there. All right, here's another pretty bad drawing of normal and tangent, but there it is. We have a tangent and a normal here, and we see the right angle there. All right, here's an application of tangents and normals. Imagine a cyclist going around a track with a curved bank, right? When this dotted line represents the cyclist, sorry, and as they're biking, there are forces here. We're talking about physics. There's a force that's keeping the cycle or the bicycle or the cyclist pinned to the track. If there's not enough force to keep him down, then there's outward force as well, and the force can cause them to slide along the tangent line. So this is the normal line, this is the tangent. They will slide along the tangent if there's not enough force here. Okay, let's take some notes now. We're going to do some problems together. First, a tangent to a curve is a line that touches the curve without crossing over. All right, or it intersects at one point. That's the way we've been labeling it. A normal to a curve is a line that is perpendicular to the tangent line. When lines are perpendicular, the slopes are negative reciprocals. So that's just recapping some of the vocabulary and the ideas we've just talked about. All right, so here's our first example. We have a parabola here, concave down, and we're going to find something at this point. So here's our equation. How can we find the slope of the tangent line? So let's say we want this slope of this tangent line. Well, I hope you're answering, well, we just find the derivative. So I found the derivative of that one, and it's here. And now that I have the derivative, I have to figure out where that point is. If I look at the graph here, it looks like that's x equals 1. So I'm going to put 1 in there into the derivative, and that produces the slope of the tangent line, which is 2. Okay, so the x value goes into the derivative, gives us the slope of the tangent at that location. So now we have the slope. Okay, next question. How do we find the equation of the tangent line? Okay, well now we have the slope of the tangent line, and it is a line, so we already know when we have the slope and we can find some other point, then we can create an equation of a line. So what do we know a point? Well, we do. We know this point right here, the one where x was 1, but we don't know the y value there. We can see it on the graph, but if we didn't have the graph, how would you find the y value? So to find the y value of that point, we put that x value into the original function, right? A lot of students get confused here. They just start mixing things up. We put the x value into the derivative to find the slope, but we put the x value into the original function to find the y value at that point, right? So 1 goes into the original function like this, and we get a value of 3. That means the coordinates of that point are 1, 3. So now we have a slope and we have a point. And once we have a slope and a point, there's the point right there, we can find the equation of the line using this rule we talked about, y minus y1 and m times x minus x1. Create the equation, put the 3 in there for y, put that in for there, and we've done this work in the previous units. Simplify if you want to, put it all on one side, and we have this equation of this line. So that's the equation of the tangent line. Okay, let's take it a step further. Let's find the slope of the normal. Well, the normal we learned is perpendicular to the tangent, right? So this is perpendicular. And we know the slope of the tangent is 2 because we just found it. So what's the slope of the normal? Slope of the normal must be negative 1 over 2. It's a negative reciprocal. So now we have the slope of the normal, and next step, we want the equation of the normal. So how do you find the equation? Well, just like we did before, we know the slope of the normal, we just found it. And we know a point on that normal line because it's the same point here that we used for the other equation. So using that slope and that point, we can create the equation of the normal. So we use that rule for creating the equation of the line. We put 3 in there and 1 in there. Simplify a little bit, try it now, and you should get your equation of the normal. Okay, so those are the basic steps. If you know how to create equations of lines and you understand that the derivative gives you a slope, then you have all the tools you need to figure things out. So let's try this one. Try this one out. Try A, B, and C here. Okay, that was your first time on your own trying this out, so let's see how it went. Here's the equation of the tangent. Here's the equation of the normal. Check the work carefully if something did not go right. Okay, let's try another one. Here we're given this function. It says find the gradient at x equals 0.5, so that means find the slope at x equals 0.5, and then find the equation of the tangent. So try the same steps as we did before. Let's check our work. Here is the gradient function, the derivative. Then we put 0.5 into there to figure out the gradient when x is 0.5. So now we know the gradient, but now we need a point. So the point is 0.5 and 3. When you put 0.5 into the original function, you get a value of 3. So putting the x value into the derivative gives us the slope, and putting the x value into the original function gives us the point that we're going to use to create our linear equation. So here's that slope, and here's that point, and we have our linear equation. Check your work. This is the line, so here's the point of tangency, 0.53, which we see here, x value of 0.5, y value of 3. And then here's that tangent line that we found the equation of right here. All right, next, try this one out. This one's a little different. It says we're looking for the coordinates of the points of this graph where the gradient is 4. So this time it's telling us the gradient. Think about what that means. When we found the gradient function, we could find the gradient by putting x values in. But now we're told what the gradient is. So find the gradient function and set it equal to 4. Then solve that, and you'll find out when the gradient is 4. Let's check. So here's our original, here's the gradient function, and I set it equal to 4. Because I'm basically saying, remember the gradient function represents the slope. So I'm saying, when is the slope equal to 4? When is the slope equal to 4? Solve this by factoring, and you get 4 and negative 3. So that means when x is 4 or x is negative 3, we have a slope of 4. This 4 here and this 4 are coincidental. Don't think there's a pattern here. So we found out at those two places the slope is 4. So now those are not the coordinates though. Those are just the x values. The coordinate means give me the y value as well. So what's the y value? Well, the y value you find by putting each of those points into the original function. So I put 4 in the original, I put negative 3 in the original, I got those two y values, so now I have my full coordinates here. Let's look at the graph of this one. I think it's important to see. So the red curve is the original function. Here are two tangent lines representing two locations on the curve where the slope is 4. And you notice those 2 points are the 2 points that we found here. And they have the parallel slopes of 4. This question, please read it. Think about what it means. A horizontal tangent. That means the tangent line is horizontal. What is its slope? Well, the slope is 0 when it's horizontal. So follow the same process as the last question. Find the derivative, put 0 in for the derivative to find out when the derivative is equal to 0. Let's check our work. So here's the work for that. Here's the derivative being set equal to 0, finding the locations, and here's the graph. You can see two horizontal